It's natural to wonder what the big deal is whenever a technology starts trending. Progress isn't always linear. So I'm going to help you wrap your head around Iceberg by showing how the story unfolds. Maybe you've seen web pages like this, and YouTube videos like this, and presentations like this. If Iceberg is simply about tables and we've had database tables for 50 years, then what's the big deal? Let's do a quick history lesson. This was IBM's big seller in the 1960s, but to use it, you had to understand its storage. Its data model resembled a tree. Here I get the demographic segment for a patient. Then I get the next illness for that patient, and then the next care for that episode. And I continue to walk the database to sequentially access data stored within the tree. The IMS data language was used to extract values. There's code to get data from each segment. This procedural system required a programmer to specify how to navigate the data structures. There had to be an easier way, and this paper changed everything. Future users shouldn't need to know how the data is organized. Relational tables plus SQL was the solution. A query optimizer determines how to extract values, so a non-programmer only had to describe what result was desired. As important as the relational model was, how it was implemented was just as important. It took an entire system to enable concurrent readers and writers to reliably access the same table. If we have a sales table like this, and we change this customer ID by submitting this SQL, it looks like the value gets instantly overwritten. But there's a lot of magic going on under the hood to ensure our transaction is processed reliably. Our table's data and index are on disk. Locate the block with the incorrect row, copy the block into memory, update the header to lock the row, copy the old value to the undo buffer and to the redo buffer, copy the new value to the redo buffer and to the block in memory, and write the buffers to disk so the old value finally gets overwritten. This complex process ensures our transaction is ACID compliant. It was a hard problem, but it was solved 50 years ago. So why did we need something new? Something must have changed. Something physical must have changed. A traditional database system with its monolithic design and tightly coupled layers worked great, but sometimes data volumes outgrew processing power. Hadoop was an alternative, but it began as a Java project to analyze HTML gathered by a web crawler. So to use it, a programmer had to write complex Java programs. And Hadoop's file system was designed primarily for data retrieval. Hive was an attempt to make Hadoop user-friendly with a SQL interface, but jury-rigging a platform designed to process unstructured data was suboptimal, and the append-only nature of the file system prevented Hive from being ACID compliant. Unlike a relational database, Hive did not enable record-level updates. As Hadoop migrated to the cloud, data moved to object storage, where files couldn't be changed. Apache Hive was the first open table format. It was started by Facebook back in 2007 and open-sourced a year later. Because Hive didn't age well, multiple projects attempted to develop a better table format. The first attempt was started at Uber in 2016, and the project's first name was spelled hoodie, like the sweatshirt, as shown on this old Uber slide. Hoodie was primarily designed for updates and inserts in Hadoop. The Apache Iceberg project was started at Netflix, and as many vendors point out, Iceberg is fully open, vendor-agnostic, engine-agnostic, and maintained by an entire community, not by one vendor. Delta Lake started out under the name Databricks Delta, and it was a proprietary feature for Databricks users only, until it was fully open sourced in 2022. Which one of these names is not like the others? The Apache Way is a set of guiding principles used to govern the Foundation's projects. It requires software to be vendor neutral, but Databricks completely controlled the direction of Delta Lake, so it couldn't be an Apache project. But last year, Databricks jumped on the bandwagon by acquiring a startup focused on Iceberg adoption. Now we'll go under the hood. The project's name and logo hint at its architecture. A catalog is the only visible portion of an Iceberg table above the waterline. These components solve the hard problem of enabling table semantics on a collection of files. An analogy will help. A catalog is like a logbook with pages for all of a ship's voyages. A bookmarked page contains data about the current voyage. That page references an inventory of all the ship's containers, which references a packing list for each container. And each item inside a container is like a data file. A database is often used for the catalog. Table metadata is formatted in JSON. Manifest lists and files are Avro, and data files are usually Parquet. You'll often see these referred to as layers, where the catalog points to the current metadata and the metadata points to the associated data. Before I began to use Iceberg, the only container I needed to provide was an empty folder. When I called an API to create a namespace and a table, folders were automatically built for them. The system created a catalog database and folders for the metadata layer and for the data files. When I ingested data, it was automatically partitioned based on a spec I included in the table's definition. As I grew the table, more Parquet files were automatically written to each partition folder. Here you see examples of each metadata type. An all-in-one database server didn't need to integrate multiple compute engines with its metadata and data. But Iceberg does, so it can be implemented in many ways, and I'll show examples where different engines are used for ingesting versus consuming. Here's an example of using open source software in your own data center. Polaris is the catalog, and Flink is the engine used to write data into S3 compatible storage. A different engine, Trino, is used for queries. Here's a closed source system. Databricks is used to ingest data, and Snowflake is used to query it. Or you can use Snowflake for ingestion and Databricks for consumption. Here's an example of native services from a single cloud platform. And here's the setup I used on my laptop for testing. It was wonderful to do research without needing web services, a Docker container, or even a JVM. I'll conclude with a use case demo, tracking sales for a furniture shop. My first step was to create an empty table by sending specs to an API. After the table was created, I queried the catalog. Just like how there's a bookmark to point to the current voyage, the catalog points to the current table metadata file. If I had other tables, my catalog would contain a row for each. What's inside a table metadata file? There's a schema which defines the table. This partition spec shows an example of Iceberg's hidden partitioning. I didn't have a separate column with the partition values. Instead, I told Iceberg how to derive them at write time. A sort order will help engines skip unneeded data when filtering by that column. And you can provide custom properties like the maximum number of rows for each Parquet row group. Next, I ingested data from 100,000 records by copying them to an in-memory table and then calling an API to append them to my Iceberg table. This caused my catalog row to point to a new table metadata file. This atomic swap operation helps make Iceberg ACID compliant. The new table metadata shows that a snapshot was created. 100,000 rows were written to 4 files across 4 partition folders. and metadata points to a manifest list. The list represents a snapshot of the table at a given point in time. It contains the path to each manifest file in the snapshot. For this step, I had one such file. A manifest file points to each Parquet file that makes up the snapshot, and it contains details about each, like its row count and row group offsets. 4 partition folders were automatically created, and each was populated with a Parquet file. So the current table snapshot consists of these 4 data files. When we look inside one of the Parquet files, we see its useful metadata, like counts, the schema, and the fact that each full row group contains 10,000 rows, as I specified. This metadata for one row group and column shows min-max values to help prune unneeded data at query time. I use DuckDB to query my table. You never interact with a table at the file level. You use a query engine that treats your snapshot of files as a single table. Here's a simple query to see what my rows look like. I counted rows by my hidden partition and saw that 10% of them are errors. Here are a few examples, and I don't need to keep this kind of data, so my next step was to remove them by calling an API to delete rows based on a filter. Let's look at the list that was created when I submitted the delete request. Because all my errors were stored in one partition file, Iceberg simply changed that file's status to deleted, and the status of the others were changed to existing. So my remove action was simply a metadata change. And now queries against the new snapshot would only scan 3 files. So when I do a count again, we see the errors have been removed. Iceberg enables time travel, so we can still see what the table looked like earlier by querying the first snapshot. Another Iceberg feature is schema evolution. The business expanded to multiple locations, so a new store ID column was needed. When you evolve a schema, you simply create a new version. Just like how table metadata can track snapshot versions, it can also handle multiple versions of a schema. After appending the new column, the existing rows did not have store ID values. We can use time travel again to see what the rows look like under the first schema. Next, I inserted new records, and each included a store ID. A new Parquet file was added to each partition folder, so the new snapshot now consisted of 6 data files. A count shows that about 50,000 new rows were spread across 4 store IDs. The original sales were made at the First Kentucky store, so I needed to update the store ID for those rows. I called the overwrite API, but remember that the Parquet files are immutable, so my update was materialized by deleting the old files and adding new files with the store ID populated. My final snapshot was made up of these 6 data files. My final step was to repeat the count, and it showed that each row now had a store ID value. I'll close with this visual reminder that Iceberg sunk the competition, and it's gaining momentum.